Hello, everyone. Welcome to week 1 of the series, R is for Actuaries, presented by the Quarantine Coding Academy, QCA. This is a 4-part series designed to serve as an introduction to R for actuaries and technical folks in general. This course is designed for someone who uses a lot of Access and/or Excel in their current role and is interested in alternative approaches. The topic for week 1 is data prep with dplyr. We will unlock a lot of R's power by learning just a few simple commands. As the course progresses, each week will build on what we learned the prior week. By the end of the course, you will have put together a full stack project, from raw data to final report with interactive dashboard, all without leaving R. Now, let's get started with week 1. Coding in R is really just calling a series of functions. There are thousands of functions available in R, and the total increases daily. This is what makes R so powerful, but also so intimidating. Some functions are available just by opening R, but it would be inefficient to include them all. You need to determine which external functions you want to use for each project. Lesson 1 attempts to simplify R a little bit. We'll focus on only 6 functions that will address the majority of common actuarial needs. These functions, along with others not covered here, are bundled together into the dplyr package. Terminology, a package is simply a bundle of external functions. The 6 dplyr functions we will cover in lesson 1 are group by and summarize, which are used together to get totals by groups. Mutate, which is used to add a new column. Interjoin, which joins tables together. Filter, which filters on specific rows, and select, which selects specific columns. So that's it for the background information. Let's begin our script. Before we get started, you need to set up an empty folder that will be dedicated for this project. Once you do that, copy these 2 CSV files to this folder. I'll put these links in the comment section below so that you can just click and/or copy and download these files. You should pause this video until you finish this step. Whenever you create a new R script, these are 3 steps you should take to create that script. 1, you should create a dedicated working directory, and you should save your associated data here. That's what we did here. 2, open RStudio. Open a new script and save it to the directory that you created in number 1. 3, set working directory to source file directory. Source file directory is the directory we created in step 1. Once you do these 3 steps, you're ready to start coding. So let's walk through those steps. The first is to create our dedicated working directory and move our data files there. You can see I have a folder that I called week 1, and the only 2 files I have saved there are our 2 CSV files, mortality and value mapping. Next, we open RStudio and create our new script, which we saved to this directory. We do that by hitting start, typing in RSTU. Once RStudio opens, we create our script file, new file, R script. We save it to our working directory, file, save as, and navigate to the directory that we created. So for me, that is C, QCA, week 1. You can see only the 2 CSV files are there. You need to name your file. I'll call this one week 1. And now you can see that our script is called week1.r. And if we look at our working directory, we see that there's a file there. So R knows that our script is saved here now. But what R doesn't know is that we want it to look here for data. In order to do that, we do step 3, which is session, set working directory to source file directory. So we're setting our default directory to the same file as where our script is saved. And because we saved our data and our script to the same file, this will prove to be convenient. So now that we've done that, we're ready to start coding. First, install the packages that you will need for this specific project. This can be accomplished with the following snippet of code. Deconstructing this code, you can interpret the install.packages function as save a local copy of this external CRAN package. You can interpret the library function as, for this working session of R, activate this locally saved package. Now notice how R is structured. Function, argument, function, argument, function, argument. We'll see this theme continued throughout our four lectures. Things to keep in mind, you only need to install a local copy of a package once. You need to activate selected packages every session. Best practice is to begin any script with the packages you will need for your task at hand. For this exercise, we need the dplyr package, no surprise, and the data.table package, which will be explained why below. So if we want to run this code, we would type it in our script, or in my case, I'll copy and paste. And to run a line of code in R, you have your cursor anywhere on that line, beginning, end, middle, doesn't matter. You hit Control Enter. It runs that single line. So we run both those lines. We see that they ran. And what we did was we activated the dplyr package and the data.table package, which means that for this session of R, we have access to any of the functions that are part of dplyr or data.table, as well as internal functions. Next, import the data sets that we will be working with. This can be accomplished with this snippet of code. Let's deconstruct this snippet of code. When you see a left arrow, you should interpret that as create a new object. Note, there are two functions that are used for reading in our data, fread and read.csv. Interpret read.csv as import into this active R session this file. Import fread as import into this active R session this file, and do it faster than read.csv would. Now, you may be asking yourself, why not just use the quicker fread every time? Well, fread is not internal, and it requires us to load the external package data.table. Read.csv is internal, so this is why we had to install data.table. So you have to decide if that external package install is worth the added speed on your import. And for us, this is such a large file, it's worth it. So let's translate this code to English. Create a new object, call that object data.value. Create it by not so quickly reading in value mapping.csv. Next, create a new object, call that object data.mortality. Create it by quickly reading in mortality.csv. This code snippet involves two lines, and they each need to be run separately. And I'll get more into that a little bit later. Note that we did not need to specify a directory for our CSV files, and that's because they're in our working directory, which we specified in step 3. So that is convenient. Now, once we import it, we'll see in our top right-hand console that we'll have two new objects, data.mortality, data.value, and the dimensions are 1,472,599 rows by 34 columns and 7 rows by 2 columns. So let's run this snippet of code and see. So we type or paste it into our script. We run both of those. And we do see 1,472,599 by 34 and 7 by 2. data.mortality, data.value. So we have these two new objects as intended. Next, calculate total deaths and expected deaths by count for each valuation year. For expected deaths, use the 2015 table. This can be accomplished with this snippet of code. Let's deconstruct this code. The first thing you probably notice is this percent greater than percent sign. This is called a pipe. If you see this symbol, you know that dplyr is being used. Whenever you see a pipe, just interpret it as saying then. Code snippets that are piped together will be run together, unlike the data import above. As a review, this left-hand arrow should be interpreted as create a new object. When you see this dplyr function group by, you can interpret that as combine your data set into these levels. When you see the dplyr function summarize, you can interpret that as sum totals within each group by cohort, and these are the values to sum. Now let's translate this code to English. Create a new object. Name that object data.grouped. Create it as follows. Start with data.mortality, then group by valuation year, then sum deaths and call that actual, sum this 2015 DBT policy column, call that expected. And these should be summed by levels in this group by cohort. Once we run it, we'll have a new object called data.grouped. This object will have 7 rows and 3 variables, the 7 rows corresponding to the levels of valuation year, and the 3 columns being the valuation year, actual, and expected. So let's run this snippet of code and see. So 7 rows, 3 columns. And if we click on it, we see that the rows are for the valuation years and actual and expected as intended. Next, calculate the actual to expected mortality ratios by valuation year. This can be accomplished with this snippet of code. Let's deconstruct this code. You can interpret the dplyr mutate function as create a new variable defined here. In this case, the new variable is called A to E, and it's defined as actual to expected, or actual divided by expected, excuse me. Translating this code to English, create a new object, call that object data.grouped. Create it by starting with the existing object data.grouped, then create a new column, call that column A to E. Define that column as actual divided by expected. Once we run this code, the object data.grouped will have an additional column. Let's run it and see. Putting it into our code. Now, before we run it, let's look at data.grouped. It has 7 rows, 3 columns. So we would expect it to have 7 rows and 4 columns once we're done, which it does. And the additional column is our A to E, which is, over 1 and less than 120 for every year, which seems reasonable. Next, we want to map the 7 valuation years into 3 hypothetical underwriting regimes, defined as follows. Valuation year before 2012, regime A. Valuation years 2012 and 2013, regime B. Valuation years 2014 plus, regime C. This can be accomplished with the following snippet of code. Deconstructing this code, we see this new function, this new dplyr function, inner join, which we can interpret as perform an inner join on the previous table with this table and join by this column. This is the most common type of join that I use. It's used for me for mapping when I do a mapping, and that's what this is accomplishing. There are several types of joins. Just know that R is capable of accomplishing all of them, and I don't want to get into the details of all of them here. But know that R can handle any type of join. Once you run it, you'll wind up adding a new mapping column to your data.grouped object. So let's translate this code to English. Create a new column. Create a new object. Call that object data.grouped. To create that object, start with the existing object data.grouped, then join to the data.valYear table and join by the val.year column. As with everything in R, there's more than one way to accomplish this task. The code snippet below demonstrates the use of the if-else command in conjunction with the mutate function, which we already saw. The end result is the same, so both methods are correct. A table will make more sense when you have a lot of levels to map. Example, if you were going to map states to regions, you wouldn't want to type all that out in an if-else. While an if-else might make more sense if you have just 2 or 3 levels and you don't want to create an external CSV file. And note there are other ways of accomplishing this as well, which you'll learn as you explore R on your own. Now, how you accomplish this is a personal choice. It's up to you however you want to do your work or your homework. Now, this is the code snippet that will accomplish this, and let's deconstruct this code snippet. The first thing you might notice is the use of the double equals sign. Double equals sign is used for conditional statements, whereas single equals is used for assignment. So in the if-else, we're checking for equality. It's conditional. It's creating a Boolean. Whereas this equals sign, like we saw in the prior mutate example, is assigning its name to this column. So assignment versus conditional. Next thing you might notice is this vertical symbol here. This vertical symbol means or. If you wanted to use the and statement, you would use the ampersand. The next thing to keep in mind is that if-else works identical to the Excel if statement, where the syntax is if-else, condition, output if true, output if false. So translating this code to English, create a new object. Call that object data.grouped. Create it by starting with the existing object data.grouped. Then call that column underwriter2. Underwriter2 as if valYear is less than 2012, define it as A. Otherwise, if valYear is equal to 2012, or if valYear is equal to 2013, call it B. Otherwise, call it C. Both these snippets of code and compare them. So we will add the first snippet, and we will add the second snippet. So let's add the first one. And we added a new column to our data.group called underwriter. And it has it mapped to A for the first 3 years, B the next 2, C the next 2, as we intended. Now, when we run our next snippet of code, we will see that we added a second version of underwriter regime, and you'll see that they all line up the same. So we got to the same place through 2 different methods. So there's one correct answer, but many ways to get there. And this is just 2 ways. There are infinitely many more. And that'll be the case with just about everything you do with R. So next, we only want to look at valuation years where the number of deaths is at least 2,000. This can be accomplished with this snippet of code. Deconstructing this code snippet, you can interpret this dplyr filter function as only look at rows where this is true. So translating this code to English, create a new object, call that object data.grouped. That object should be created by starting with the existing object data.grouped, then only look at columns where the actual entry is greater than 2000. When you run filter, your resulting object will be less than or equal to the original number of rows, and the number of columns will not be impacted. So let's run and see if this performs as intended. Entering it into our script and running it. Now, first keep in mind, data.group, 7 rows, 6 variables. So we should not see a change to the 6 variables, and the 7 should stay the same or decrease. Running it, 5 rows, 6 observations. So initially, it seems reasonable. Let's look at it. And the thing we notice is that what's left, all the actuals are greater than 2000. So it performed as intended. Next, we want to remove the redundant column under writer 2. This can be accomplished with this code snippet. Deconstructing this code snippet, the first thing we notice new is this C function, which is the combine function. This is used to create a vector of elements that you define in the arguments. You use this to apply a function over several arguments, such as several column names, like we're doing here. You can interpret the dplyr function select as select only the columns that I define here. So translating this code to English, create a new object, call that object data.grouped. Create that object by starting with the existing object data.grouped. Then select only these columns. As in our prior task, there's more than one way to complete this. And the additional way, and perhaps an easier way to do this, instead of defining the columns you want to keep, you might want to define the columns you don't want to keep. So you do this by listing the columns you don't want to keep and just adding a negative sign before the C. So translating this snippet of code, we can interpret it as create a new object, call that object data.grouped. Create that object by starting with the existing data.grouped object, then select all the existing columns except under writer 2. Now these should wind up with the same results, and you see that create data.grouped A and data.grouped. So let's run them and compare and see if we get to the same place, just to be sure. So we'll put the first one into our script, and then we'll add the second one to our script. And running data.grouped A, this is 5 and 5. Data.grouped 5 and 5, same dimensions, but let's see. And we see that there's no under writer 2 like we had before with data.grouped. And if we look at data.grouped A, same thing. So these are these have the same columns, different order, but that's just from the way I listed them in my C function, but you can see that they have the same columns. So these are the same data sets. So this performed as intended. So let's summarize. What have we done? We've now taken our original data set, data.mortality, then we grouped by valuation year. Then we summed the actual and the expected death. Then we added a new column, which we called A to E. Then we joined the value year table. Then we filtered out rows with less than 2,000 deaths. Then we removed a redundant column. Now, you saw that this was all done sequentially on the same data set and the same object. We called it data.grouped. and we just worked on that. And this is a good representation of how code is created. It's very piecemeal, very iterative, and it's very rare that you're going to go into a project knowing all the tasks you're going to need to complete, and the order that you're going to need to complete them. Ultimately, however, you do get to your final result, just like we did in our simplified example above. Well, at this point, you could use dplyr and the pipe operator to clean up and chain all that code together into a more production-like format as follows. This snippet of code will replace everything that we did up till now. Deconstructing this code, you'll see that there's nothing new here. We just chained or combined, piped, whatever you want to call it, all the steps into one snippet. And some things to know, like with dplyr, it's all sequential. So you can create a new variable in one line, and on a line below, use these variables that didn't exist before that line. Very, very powerful. So translating this code to English, we can see that what we're doing is we're creating a new object. We're going to call this object data.change. We create it by beginning with the existing object data.mortality. Then we group by the valuation years. Then we sum our deaths, and we call that actual, and our 2015 expected deaths, we call that expected, and those are summed by the levels of valuation year. Then we add a new column. We call that column A to E. We define that column as actual divided by expected. Then we join on the data.valuer table, and we join on the column val.year. Then we create a new column, call that column underwriter 2. We define that column as if valuation year is less than 2012, we define it as A. Otherwise, if valuation is equal to 2012 or 2013, we define it as B. Otherwise, we define it as C. Then we only look at rows where the actual number of deaths are greater than 2,000. Then we remove our redundant underwriter 2 column. Or in other words, we look at all columns except for the redundant underwriter 2 column. Excuse me. So that snippet of code replaces all the operations that we have worked on before this. And it looks much more elegant and efficient than the piecemealed approach that we had done. But like I said, it's nearly impossible to conceptualize without going through some iteration. But it also demonstrates the potential of dplyr. You can, like I said, several data manipulations can be coded to happen sequentially and very quickly. Now, the 6 functions that we demonstrated here are only a glimpse of what dplyr and R can do. As you begin using R for more tasks, you'll discover many more useful packages and functions. And as you go along, Googling when you're stuck is encouraged and really the best way to learn. Now, let's run this code just to verify that it does replace what we've done before. So if we copy it, paste it into our code. Basically what we're doing is we're starting with data mortality, just like we did at the beginning of our task here. And we're going to run all these lines together so that hopefully our data.change is the same table as this data.grouped. So let's check. And they're both 5 observations, 5 variables with over 2,000 deaths, 11 through 15. So these objects are the same. So this section of code, if you went through and decided that after going through iterations and you came up with this as your final process, and you decided now we went from experimental to production, this is what production code would look like, generally speaking. So this concludes the presentation. Now the next step is homework, which we want to complete this because we'll use the homework for our visualization next week. So what I want you to do before the next lecture is to calculate both count and dollar-weighted actual to expected mortality ratios, first by banded age, and banded ages are defined below, then by banded age and by gender, and then by banded age, by gender, by smoker status. And I want you to do this for each of the mortality tables in the data set. There's 5 of them. These are the mapping rules for your banded ages. Address that however you see fit. When you do that, save your file as a R script, and you should have 15 different objects once you're done. 3 summaries using 5 tables. And we'll be building on this script in our next in our class next week, which is data visualization with ggplot2 and plotly. And remember, like we saw in our example, and like we will, same thing for the homework. There's many ways that you can do this. So, I'm not going to grade on, or it doesn't matter how you get there, but there is a correct answer. So that's how, that's the important thing, is getting that correct answer, not necessarily how you get there. So I'll provide a sample solution with material that gets put out for the next lecture, and then we'll visualize this in our next lecture. Thank you.